Okay, well, welcome. You're in the machine learning class, which is 10601. And there are a couple different machine learning classes this semester. So if you think you should be in a different machine learning class and you accidentally came to the wrong one, my feelings won't be hurt, but this is the one we're in right now. My name is Tom Mitchell. I'm one of two professors who are going to be team teaching the course. The other is Nina Balkin, and I'll introduce her and the other TAs in a moment. But I wanted to just start by welcoming you and saying a few things about machine learning. And if I can, I have a new laptop computer, and I'm still debugging my own skills for using it. So every once in a while, you'll see odd things happen on the screen. So like this, what's this about? It's not even on my screen, but that's okay. So machine learning is a subject close to my own heart. It's about the question of how do we build computer programs that automatically improve what they're doing through some kind of experience. So to have a well-defined problem in machine learning, I'd say we need to have three things specified. We need to have some performance task that the computer is performing, and some metric for what it means to do that better or worse, and then some kind of experience from which the program can train. So for example, you're very familiar with spam filters, and you're probably aware that spam filters are trained using machine learning. So if we took that as an example, we'd say the task is to take an arbitrary email as input and produce a label, spam or not. That's the task. The performance metric we would like to optimize, I could make up several random spam filter programs, but there's some performance metric that, for example, you know what your own spam filter, your own notion of spam is. And so there's some, if you were, for example, to label a set of emails as ones that you consider to be spam or not, then we could say our performance metric we might use to make a well-defined learning problem is to match as closely as possible the labels that you've assigned to the emails. That is for the program to learn to match as closely as possible your own labels. So that would be a performance metric. And the type of experience, well, it could be just what we said. It could be the experience the program's going to learn from is a set of labeled emails. This one's spam, this one's not spam, here's another spam. And so there's an example of a well-defined machine learning problem. We can make another one, also with spam. We could say, for example, we could change the performance metric. Maybe you don't really want to minimize the number of errors the spam filter makes compared to your gold standard. Maybe you actually are more worried about losing a good email into your spam folder than you are about accidentally looking at what is actually spam. So you might actually have a slightly different performance metric that you'd like to optimize that gives a bigger penalty if the program accidentally labels non-spam as spam than if it does it the other way around. So that would give you a different, again, well-defined problem. We also could change the experience. So for example, so far we're talking about training a spam filter by giving examples of emails with labels, spam not. Some computer programs, and we'll learn about them this semester, can also take unlabeled examples, unlabeled emails, as additional data. And there are algorithms that can perform better, learning algorithms that can learn better if they're given both those labeled examples and a whole bunch of unlabeled email, which seems kind of like magic. But by the end of the semester, you'll understand what's the principle underlying that. And in fact, what kinds of situations, what kind of formal structure a problem could have that makes unlabeled data be actually useful for training a spam filter. And spam actually is an example of a problem that has the structure that makes unlabeled data useful. Okay, so there's, roughly speaking, what we mean by machine learning. We could make up a lot of examples of machine learning problems and characterize them this way. We talked about spam. We could also talk about self-driving vehicles. Suppose we want to make a self-driving vehicle learning system. It's going to, for example, learn, given the camera and other sensor input, it's going to learn what direction to steer and whether to step on the brake. So that'd be another function, actually. Just like the spam filter was a function from emails to labels, here my robot would be a function from sensor observed data to recommended control actions. So let's see, if we wanted to make that a well-posed problem, then we'd have to say what the task is. I guess I just did that. We'd have to say what our notion of performance is. Maybe we want to get you to school, to class, to CMU on time for noon for class. In every case, no matter where you start out. And the fraction of times that you're late for class would be the penalty function. And what kind of experience? Well, again, we could do that several ways, but the most supervised kind of experience you could imagine would be if we trained the car by actually driving it and letting it observe our own steering and brake commands while it was also perceiving the sensory input. And that way it could construct a large set of labeled examples of here's what my sensory data is, and in this case the person, the trainer, did this steering command and this brake action. You get a large set of that. In fact, if you're training a car, I recommend that kind of training instead of, say, letting it drive randomly and crash into things. But you could imagine, again, there are different variants on how we could set that up. Okay, so that's machine learning in a nutshell. It's about how do we build computer programs that perform some task and improve their performance in some well-defined metric according to some type of experience. So during the yeah, good. I see what's going on here. So let me just quickly go through a number of examples of problems of the type that you will be covering algorithms that you'll be familiar with by the end of the course. So for example, one common use of machine learning methods is to do what people call data mining historical databases. One example could be medical records. This slide describes a project we did with McGee Hospital here in Pittsburgh some time ago, which has a large database of medical records for babies being born. And from that historical record, they have many examples of the medical state of the mother during the 9 months leading up to the birth, and then an indicator about the birth. And they were interested, for example, in whether the birth would happen as a normal birth or as a birth that requires surgery, called a cesarean section. And so this slide just shows an example of using machine learning to learn rules that characterize, in this case, if you're a prospective mother and happen to have these 3 symptoms, then your chance of having a surgical birth instead of a natural birth is 63%, at least in their database. So this is an example of mining historical data, structured data in this case, structured in the sense that the data is described by a set of fields with values, unlike, say, images or sounds, which I would we'll refer to as unstructured data. And this is just one of thousands of examples I could have shown you of mining historical databases. So another very common example you might be familiar with is when you swipe your credit card to buy something in the store and the computer decides whether to approve or not approve your purchase. That's because there's a very sophisticated strategy that's being automatically applied to the data about your particular swiping of the credit card. And that strategy is the result of a machine learning algorithm running on a historical data set of millions of credit card transactions. Some of them turned out to be labeled as, eventually as fraud, others being labeled as legitimate purchases. And again, there's a wonderful and very practically valuable machine learning problem, almost isomorphic to this one, if you think of them both as just examples of historical records of data labeled in some way where we would like in the future to be able to take a new record and predict those labels. Okay. In addition to structured data, we're going to be looking at unstructured data like text. Here's an email that happened to show up yesterday as I was preparing this lecture, very entertaining email. My spam filter correctly labeled this one as spam. But if you think about it, to write a computer program to analyze text data requires a different kind of representation than more structured data. And we'll be looking at that. Also at images. Many of you have now phones that take pictures. You might have noticed, at least on my phone, when if I were to take a picture of this class, we could, I should do that. You put little boxes around all your faces. That's because cameras today can actually find faces automatically in the images. And this slide was given to me a number of years ago by Henry Schneiderman, a professor here in robotics, who since has left to build a startup company on his face recognition software, a successful one too. But it's just an example of another machine learning task where, in this case, we're trying to learn a function where the input is an image and maybe even a region in the image, and the output is a label, face or not face. Maybe even a couple different labels, face, not face, or a face looking straight at you versus a face looking to the left. Here's another one. This is a picture of brain activity from an fMRI scanner for 15 seconds while a person reads a word. And these are different locations in the brain. There's the time series of activity in the brain. In my own research group, we use this kind of data, and we do things like train a classifier, in this case, to determine whether that word the person was reading was a noun or a verb. And it turns out that's possible too. And this is an example of a kind of problem where computers are actually much better than people. So I've tried to look at these things and see if I could train myself to distinguish whether somebody was reading a noun or a verb, and I cannot do it. But my program is much more competent than I am after it trains on the data. I'm going to skip that one. Okay, so the bottom line is there are a lot of practical applications of machine learning. In this course, we're going to cover examples drawn from this. There are also a lot of different machine learning algorithms that have been developed, largely driven by people's interest in solving these practical problems. And you're going to learn these algorithms as well. In addition, you're going to learn not just about the applications and the practical algorithms, but something about the underlying theory. One of the most, I think, interesting sets of theoretical questions in computer science are really about questions about learning. So if you think about it, one of the most interesting questions that I can ask, in my opinion, is if I have some learning system, maybe it's a computer, maybe it's your brain, is there anything fundamental that relates the success of the learning strategy to properties of the training data that I present? Is there something, a way we can formalize that question and turn it into something about which we can prove things? And the answer is yes. Statisticians, if you've taken a basic course in statistics, you're probably familiar with various kind of confidence interval theoretical results that say, for example, if you want to know the probability that a particular coin will turn up heads or tails, that's a probability somewhere between 0 and 1, that you can estimate that by flipping the coin a number of times and just observing how often it turns up heads. And the statisticians have gone beyond that to say, well, furthermore, here's a proof of some guaranteed bounds on how accurate your estimate will be for the probability of a heads, depending on how many times you flip the coin. Obviously, the more time, if you flip it 3 times or 3 million or 3 trillion times, you're going to have more accurate estimate if you flip it more times. That intuition has been turned into formal results by statisticians who can tell us exactly how the confidence interval shrinks as we increase the volume of training data for that simple learning task. But it turns out we can take the same kind of intuition and apply it to much more diverse set of machine learning algorithms. And so, for example, we'll talk in this class about a theory that relates how accurate the learned hypothesis is for some trained system, like a spam filter, for example, and how that depends on the number of training examples we present and the complexity of the hypotheses that the program considers. And it'll turn out to get a good result, a workable result. We have to talk both about the accuracy of what will be learned, its error rate, and about the probability that if we provide M examples, we'll actually succeed. So more to say about that. But the point is, machine learning is an interesting field, partly because there are a lot of interesting practical applications and algorithms, but partly because we also have the beginning of a theory to talk about properties of learning systems in general. And as we go through this in the class, think about the question of which of these theoretical results also apply to your brain. If you're a materialist and you assume the learning is a mechanical process, biological process in your brain, then you must be subject to the same information theoretic constraints that any computer program would be subject to. So, a way to think. All right, so let me just end this kind of intro with a few remarks to get us all thinking about how machine learning, this particular subfield, relates to other fields. Actually, let me find out who you are. How many people here are computer science majors? Okay, how many people here are, what else should I ask for? Art majors. Okay, none. School of Computer Science majors. That includes LTI and everything? No, okay. Help me. What else? ECE, how many ECE majors? Okay, great. How many engineering majors in general? Okay, how many business majors? Okay, good, so we have a good mix. How many people are undergraduates? Cool. How many are master's students? All right. All right, cool. So we have an interesting diversity here in the course. And it's interesting to think about how machine learning relates to other fields, including yours. here's the way I think of it. I think machine learning over the last 3 decades, I've actually been involved in this field for 3 decades, at least, has grown from a kind of laboratory curiosity to something that actually is now providing the best solutions to some of the software problems that people are interested in. So if you think of the Venn diagram of all possible software programs you could ever write, there's this niche, this subset of that, where these are algorithms where machine learning is good. For example, speech recognition, computer vision, medical outcomes analysis, robot control. These are all problems where today machine learning is the method of choice if you're going to develop a speech system. All of the speech systems in your iPhone or Android phone, those are all based on machine learning. There are other applications where machine learning is not such a great idea, like matrix multiplication. Don't even, don't try to train a program to do matrix multiplication unless you're trying to be cute. But we know the algorithms for matrix multiplication. There's no need to train a program to do it, although it might be entertaining. But if you think about what is it that characterizes the green region from the white region that distinguishes this, some of the properties are that these are applications where we have a hard time writing the programs by hand. It's hard to write a speech recognition program because we, as people, even though we can hear just fine and understand speech just fine, we actually have a lot of trouble figuring out what algorithm our brains are using to do that. Similarly, even though you could recognize me here in front of the room from the visual input you're getting, you'd have a hard time writing a computer program to recognize whether I'm the person standing here, even though you can do it. So there are a lot of things that we're good at doing for which we're not good at writing down the algorithm for it. And as computer science has evolved, more and more of those kind of problems arise, partly because we have a lot more online data and different kinds of sensor data these days. And partly because we like self-customizing software. For example, your spam filter probably has a different notion of spam than my spam filter. And that's good, because you probably have a different notion of spam than I do. And so if you think about that, or a speech recognition system, many speech recognition systems, when you use them, customize to your voice as well. And so those spam filters and speech recognition are both examples of a system that's trained once in the factory, but then once we buy it, millions of us have our own copies, it customizes to our own individual use. And the only way you're going to get it to customize is to have it improve its performance at some metric through some kind of experience. That's what it means to customize. So these are kind of reasons why I think this region is growing. All right, so let me end there for a moment. Machine learning also has interesting overlaps with all kinds of other similar fields. And what I'd like to do is maybe just ask, are there any comments, questions, thoughts about all this? I know it's kind of at a high level, but.
So
yeah.
I have a comment on matrix multiplication. So the algorithm is actually known, but there are a number of parameters that can be optimized, like the block size and the other parameters. And actually, I have now a paper in my laptop called Optimizing Matrix Multiplication with a Classifier Learning System.
Okay. If you didn't hear this, Ahmed just said he's got a paper that he just looked up, and the title is Optimizing Matrix Multiplication through
A Classifier Learning System.
A Classifier Learning System. So I've been proven wrong already about the matrix multiplication. And the reason that's interesting is that it's about optimizing the matrix multiplication efficiency, and that there are different structures of different matrices that allow different choices that will influence the efficiency. So I was mistaken when I said, don't even waste your time unless you're trying to be cute. Well, I should have said cute or efficient.
There is actually a whole field called self-adapting algorithms. You can apply to sorting, to matrix multiplication, and so on. So if you're going to do the same, if you're going to do matrix multiplication or sorting over the same type of data over and over again, you can learn from the past somehow the right structures in order to be much faster in a new example from the same task.
Cool. So the comment here was there's actually a whole field called self-adapting algorithms that, of which this is an instance. So I've been proven generally wrong, not just wrong. All right. So that was, see, I learned something in class today. That's good. So let me summarize then. Here's, if you're wondering, should I hang in there on this class? The answer is something like, it depends on what you want to learn, but if you're in this class, here's what you're going to learn. The primary algorithms, how to use them on data. We're going to give some programming assignments where you'll get to use different types of data. You'll also do a project, and you'll learn something about the underlying statistical computational theory as well. And my goal, our goal, is that by the end of the semester you should be conversant enough with machine learning and understand the basic ideas well enough that you could pick up, say, the papers in the International Conference on Machine Learning and read those and understand them. Okay. All right, so let me say a few words about course logistics and introduce our team. Here's our team. The most important thing about this slide is that it has the name of our class website. The class website will have copies of these slides too. So there's a little bit of a, you've got to write down something. After that, it's all online. So you could write down the URL for the website. I don't want to spend a lot of time on course logistics because it's all on the website and it's rather boring. But some of the important things, I know some people are on a wait list. My recommendation is if you are, hang in there and see what happens to the total enrollment in about a week or two. And you might, there's a good chance you'll get in. Homework number 1 is available today. It's on our website right now. It's due Friday. It's an easy homework assignment. And unlike most of the homework assignments, you're completely welcome to collaborate with anybody on any of the answers to any of the questions. Homework number 1 is the following thing. It's actually a test for you to apply to yourself to make sure that you have basic proficiency in several areas of math that turn out to be important for the course. So for example, there's a question on there that asks you to take the derivative of a function. What's the derivative of y with respect to x? There's a question on there that asks you to multiply a vector times a matrix, just to make sure you have a basic proficiency in that. And there are also a question on probability and statistics, questions on big O notation for complexity. And in the homework assignment, there are also pointers to remedial things you can look at, online videos for how to multiply matrices and invert them, and so forth. So the point of this first homework assignment is really to give you a chance to review those 4 areas. We are going to use them during the course. It's unavoidable because we're going to be precise, and that's the language of precision. But at the same time, you don't have to be a specialist in all those 4 areas of math to succeed in the course. So the homework will give you a chance to see whether you have the level of basic proficiency that we're going to be depending on. And if you have 3 out of those 4, you'll be fine as long as you don't mind spending some time filling in the 4th one as we go. Okay. So that's due Friday. I guess the other thing to say is, what's our policy on late homework? It's please do it on time. And it's worth half credit if it's late for 2 days and then it's not. But if something happens horrible, like you have 2 homeworks due on the same day and you forgot about that, then we're forgiving. We'll drop out the lowest homework grade during this semester. The other thing I want to say is 2 more things quickly. Notice we have the dates for the exams already. There's no outside class final exam in this course. We'll have 2 exams on these 2 dates. This is the final day of class. And the other thing I need to say about academic integrity is that I am a fanatic when it comes to academic integrity. You will fail the course if you cheat. At least fail the course. And if I can impose a heavier penalty, I will. People are often confused by that, because they think, Tom seems like such a nice guy. I am a nice guy. But I expect you to be a nice guy, too. All right, so now let me introduce my fellow instructors. And Nina, do you want to?
All right, so I'm Maria Florina Balcan. Everyone calls me Nina. And as Tom mentioned, I'll be co-teaching the course with him. I guess Tom asked me to mention a couple of words about me. So my main research interests are in machine learning and theoretical computer science. Within machine learning, I've been working on a variety of machine learning paradigms that are very relevant for the modern age of big data. This includes interactive learning, where the learning algorithm takes a much more active role compared to the classic paradigm, supervised learning paradigm, and it does so in order to minimize the need of expert or human intervention. Okay, another topic that I've been working on in the past couple of years is distributed learning, where now learning is done over massive data sets that are distributed across multiple servers or locations. And now the key challenge is to do learning with limited communication. Okay? And I'm interested in other topics such as multi-class learning, lifelong learning, and so on. And in all these cases, my main focus has been on providing algorithms with provable guarantees and also formal models in order to help us reason about how to most effectively utilize the available resources in all these settings. Okay? And as I mentioned already at the beginning, I'm also interested in theoretical computer science more broadly, and especially on connections between learning theory and other fields such as auction or mechanism design, approximation algorithms, and game theory. And of course, if you're curious about any of these, feel free to talk to me at any time about it. Okay? And our
next, Travis.
My student, my PhD student, awesome PhD student.
So I'm one of Nina's first-year PhD students. I'm really excited to take the course. I think it's going to be a lot of fun. But just to give you an idea of the kind of thing I'm working on now, I guess Tom already mentioned classification problems. And there your data is broken into 2 pieces. You have some raw observations about the world, and then some labels that tell you something about those observations. And typically when you're collecting the data to train your machine learning algorithm, usually the unlabeled data is more it's cheaper to collect. And the labels cost more because you have to get the person to label the data or the one to experiment. So it'd be really good if we could have learning algorithms that work with mostly unlabeled data. And so what I'm working on is trying to take advantage of certain geometric relationships between the different labels or concepts that you're trying to learn. And if you have them, then trying to design algorithms that can learn from mostly unlabeled data. So it's mostly theoretical, and it's part of this like active learning, semi-supervised learning research.
Kirsten.
Hi, I'm Kirsten. I'm a third-year PhD student in the machine learning department, and I'm interested in using machine learning to analyze energy consumption and then use this knowledge to reduce usage and then help people make better decisions. So right now I'm working on a project to predict residential energy costs from features of a home, which would be things like total square footage and the type of heating system that's being used, in addition to occupant behavior, which would be things like the number of people who are living in the house, and also their preferred temperature for heating and cooling. And once we have this sort of information, we can give people a better idea of their costs of living in a particular, like prospective tenants, their cost of living in a particular unit, because then we give them a personalized estimate for their energy costs in addition to the rent itself. I've also worked on energy disaggregation, which looks at a whole building power signal and wants to figure out the individual devices that are operating in that home, like a microwave or a refrigerator.
Okay. Ahmed.
Hi everybody, I'm Ahmed Kaifi. I'm a fourth year PhD student. My research is focusing on dynamical systems that evolve over time and for which you have access only to noisy observations like the GPS signal of a car or like a video of a moving object. The question I'm currently investigating is how can we gain insight into the dynamics of the system using noisy observation? How can we track and predict the state of the system? So, for example, we can here extract this oscillatory motion pattern just by looking at the video. This topic has been researched extensively. What we are trying to do is to make that able using simple models that you will learn in a few weeks, rather than waiting till the end of the course or using some algorithms that are out of scope. Thanks.
Okay. And Nicole?
Hi, so I'm Nicole. I'm a third-year PhD student in the machine learning department. And my research focuses on machine learning applied to computational biology. So basically, I work on developing new machine learning models and algorithms for analyzing high-throughput biological or medical data in order to sort of learn something valuable from that data. So for example, one project I'm working on right now is using a set of DNA markers to train a model that can predict clinical outcomes for a set of patients. So those outcomes could be anything from your risk of getting Alzheimer's disease later in life to a patient's response to drug or therapy to treat a disease that they might have.
Okay. And Willie?
Hey everybody, I'm Willie and I work on scalable machine learning. So in particular, I try to work on machine learning algorithms that you can apply well to big data sets. And even more particularly, I try to work on parallel low communication machine algorithms. So a type of parallelism in particular called embarrassingly parallel, where machine learning algorithms could essentially be split up, work independently without communicating, and then still try to combine results at the end in order to achieve like a similar result as you'd have in a typical algorithm. I don't know if I mentioned, I'm a third-year PhD student in the machine learning department also.
And Abu?
Hey, my name is Abu. I'm a second-year PhD student in machine learning. I work with Tom, and I'm working in on a project called NEL, which Tom will probably tell you more about. Basically, I'm interested in trying to convert or understand English language text or any kind of language text, and convert it from a unstructured form like sentences into formal semantic form that can be understood by a computer, and more processing can be done by that. And in this case, you can see that knowing something about the world, like forks are made of metal or vanilla is food, can tell you what relation it has with the cake and eating in these two specific sentences.
Okay. Oops. I get to go too. So I'm Tom Mitchell, and I've already said that. But I want to tell you that one of the projects I'm involved in is an attempt to ask, what would it be like to build a program that we raise over years and learns many things? So it's a kind of, you might call it never-ending learning system. Instead of training it and then turning it off, we let it go. So we're working on, with Abu and a number of other collaborators, such a program. We call it our never-ending language learner, NEL for short. And the cool thing about NEL is it turns out today is Nell's 5th birthday. It turns out we turned it on in January 12th, 2010, and it now has 90 million beliefs like these, which it has read from the web, and by some measures of performance, it's improving. Okay, so that was kind of fun, and I wanted to introduce people, and also that gives you kind of a snapshot of some of the frontier, state-of-the-art research problems that people in this field are looking at. You can feel free to talk with any of us about any of those problems throughout the semester, and we'll try on our part to build homework assignments and project opportunities that leverage from some of these problems and some of these data sets too, so that you'll have a chance to look not only at the traditional machine learning stuff, but also some of the cutting edge things. Okay. All right, so let's see. I'm going to start with the real kind of course material now. But I just want to ask again, any other comments, questions before we, yes? Sorry? The course website link again. Good call. Let me do that. There it is. It will be linked from Maria Balkan homepage too. Does anybody else notice this screen seems to have a little bit of a heartbeat, but not that screen? Okay, everybody got that? If not, ask your neighbor. Because it's time to get down to function approximation and decision tree learning. So this is the first algorithm that we're going to talk about. And I like it because it works. It's in commercial use. It's a real algorithm. And it illustrates a whole bunch of points that we're going to kind of revisit over and over through the semester in different ways about how to organize a learning system. So let's talk about function approximation. So at the beginning, the first slide, I said, well, learning is about improving your performance at some task through some kind of experience. But then if you listen carefully at the examples that I gave, most of those were really about where the task was some function from some x to some y. And much of machine learning, like I would say 90% of the papers in machine learning are really about function approximation. What do I mean by that? Here's what I mean precisely. I mean, we have some unknown target function that we want to learn we want our program to learn. And that's a function from some set x to some set y. For example, x might be the set of emails, and y might be a 0, 1 indicating spam or not. And we just want to know what the function is. And so the problem setting is that we have some set of instances. We have some set of labels, y also I should say. And then there's some unknown to the program, correct function. And the program itself has inside of it some way of representing functions, some way of representing spam filters. And that's up to you if you're designing the learning algorithm, how you're going to have it do that. But one way or another, if it's going to output a function, then it's going to have internally some way of representing those functions. And so it's useful to think of the problem setting as including that the learning system has some set of hypotheses, some functions, some set of functions, each of which maps from x to y. And in some sense, its job is to create the best function, the one that actually matches f, the unknown target function. So to do that, it gets some inputs, which are, in the case of supervised function approximation, are a set of pairs of here's an input to the function and the output of the function. So for example, here's an email and this one's spam. Here's another email and this one's not spam. Here's another one, it's not spam. A set of those examples of that function. And its job is to output some hypothesis that's within its repertoire, within its representation, that best approximates that target function f, which we never told it what it was. All we did was we showed it examples of the input and output. Okay? So this is, actually I probably should call this supervised function approximation. Supervised in the sense that our training data here is all supervised labeled data. For every email that we give it a label, spam or not. Okay, so very simple notion, but much of what we're going to cover in this course are really algorithms for doing this. From deep networks to Bayesian classifiers to logistic regression to decision trees. Okay, so to ground this, let's say the world's simplest data set here. Suppose I have a set of training examples. Each row in this table is a training example. Each row describes some day by a number of features. Most of those are weather related, and then this last one tells whether my friend plays tennis on that day or not. And so in the spirit of learning to customize individual recommendations, we might want to train a system to know what kind of day my friend is likely to want to play tennis on. So let's take that as a very simple example of training data for which we could train a supervised learning system. And let's use this to ground our discussion of decision trees in particular. Okay, so decision trees. Many of you might be familiar with decision trees already, but let's see what they are. Here's a decision tree for that function that maps from those weather features to to predict whether a person plays tennis or not. And this decision tree here, you interpret it in the following way. Given that somebody gives us a decision tree like this, it represents a function from weather features to yes or no play tennis, and it represents it in the following way. Given any example, like suppose we have an example where the output, or the outlook is sunny. Oh no. Okay, that's not apparently working for us. But suppose that, can I write it over here? Yeah. So suppose the outlook is sunny, the temperature is high, the humidity is low, and the wind is strong. So there's a day. Given that example, we can apply this decision tree function to make a prediction by starting at the root of the tree. Say, what's the outlook? Oh, that's sunny. So then we have to go down this branch of the decision tree. Then we say, oh, what's the humidity? The humidity is low. So, humidity is not low. I made a mistake there. The legal values are high and normal. The humidity is normal. So we take this branch, and now the decision tree tells us that the value of play tennis is yes. Okay, so decision tree is simply a way of taking an example, you sort it down to the leaf node that it belongs to, that tells you the value of the function. Okay, simple idea. Each internal node is a test on some discrete valued attribute in our case, outlook, temperature, humidity, wind. Each branch out of a node selects one of the values for that attribute, and then each leaf node tells us the prediction, the output of the function. And later on, we'll talk about making those probabilistic outputs. It's an easy extension. Okay, so there's decision trees. So now we can go back to our general function approximation problem. We can see that we can instantiate it for decision tree learning problem in the following way. We said we'd have a set of instances, x. Well, in this case, if we're going to use decision trees, then each of those instances has to actually be a feature vector. And furthermore, like humidity, wind, outlook, temperature, for example, in our case. And in this case, the target function, we need a value, for if it's a decision tree, then y has to be discrete valued. Why? Because the way we've defined decision tree, there's a single value at each leaf. And so as long as we're predicting a discrete valued variable like play tennis equals yes or no, or even play tennis equals yes, no, or maybe, as long as there are a finite number of values, then we can train a decision tree to, we can represent that function as this kind of a decision tree. If we're trying to predict the temperature, which could be an infinite number of values, then it's going to be an infinitely big tree. So that's why we want discrete value y's. Okay? And then we said that the learner would have a set of hypotheses. Well, in this case of decision tree learning, that's the set of all possible decision trees defined over x and y. So there could be a lot of different decision trees. This one that we happen to draw is just one of many. Okay? So in fact, now we'll come back to this definition of function approximation throughout the semester. When we talk about deep network learning, we'll see that it's another function approximation problem, but we can use different assumptions in blue, but the black stuff will still be the same. Okay, and again, then we train our decision tree learner by giving it a set of examples like those ones that we saw in that simple data table. And its job, the learning algorithm's job, the decision tree learning algorithm's job, is to output a hypothesis, a decision tree, that best approximates the target function, which is indirectly communicated to us by those training examples. Yes?
In the previous example, how do we know that the outlook is a parent node, and based upon that we classify our wind and the other factors?
How did we know what?
How did we know that the outlook is a parent node, and based on that we classified other?
Oh, in this, how did we know that outlook was the right node? We're going to talk about the learning algorithm. That was just an example tree. But this does turn out to be the tree that our learning algorithm will produce for those examples we looked at. But the question, if you didn't hear it in the back, was how do we know that this is the right tree? And let's talk about that now. What is a decision tree learning algorithm? Okay. Maybe before we get to the algorithm, let's just make sure we're all on board with decision tree notation. So here's a question. Suppose that my examples are a set of Boolean valued features. Like we had humidity and temperature and wind and so forth. They were all discrete valued. Suppose they're Boolean valued. They only have 2 values each. Then, just to make sure we're all on the same page, here's the function. Suppose my actual target function is that y is x2 and x5. These are Boolean valued x's, so they can be 1 or 0. And so x2 times x5 is the same as the and of x2 and x5. So I want y to be true if x2 is true and x5 is true. So how would we represent that simple Boolean function? Can we represent it as a decision tree? Yeah. Okay, good. So this is an easy one. We could, for example, put x2 here at the root node, and x2, of course, can be 1 or 0. If it's 1, then we could test x5. And if it's also 1, then we want to output y equals 1. Okay, and on the other hand, if x2 equals 0, then we can just stop there and just output that y equals 0. And if x5 equals 0, we can also output that y equals 0. So this function is perfectly represented by that simple decision tree. Right? So all I did was look at the fact that it can only be, y can only be 1 if x2 and x5 are 1. So I built this chain where x2 is 1 and x5 is 1. And now I output a 1. In every other alternative, I output a 0. Okay? And similarly, how would I do this one? Well, let's do it similarly. Let's put x2 here. There are only 2 possibilities. Could be 1, could be 0. If it's 1 and we test x5, and if it's 1, it doesn't matter what x5 is, does it? Good. So I don't even have to test x5. I can just stop there. If x2 is 1, I'm going to output a 1. On the other hand, if x2 is 0, then it's worth looking at x5. And if it happens to be a 1, then I can output a 1. If it happens to be a 0, then I better output a 0. Okay? So you see I can represent conjunctions and disjunctions and even more complicated Boolean functions. You can try this one at home. Now here's a question. Can you represent arbitrary Boolean functions with decision trees, or only some Boolean functions? Yes?
I think it should be arbitrary. I mean, we can represent everything. We have the joints, right? So the outputs, I mean, whatever we can think of. Either it's true or false, and we can represent that in a...
Good. Very good answer. The answer is yes, we can represent any Boolean valued function over discrete valued x1 through xn with a decision tree. And why? The simple way to see it is this. Suppose I have x1 through xn, those are all my features that I have. Those are all the attributes that I have available. Now think of the tree that's n levels deep. The complete tree that's n levels deep. That means for every possible assignment of values to x1, let's put x1 the first node. So for every possible value x1 can have, I have a branch. And then under it I have x2 at every step, and I test every possible value it can have, conditioned on which value x1 had. And then at the third level I have x3, and down at the nth level I have xn. So for any arbitrary assignment of x1 to xn of values, I have a separate path from the root of the tree down to a leaf. And so I can then say what the function value is for that very specific set of values for x1 through xn. And there will be a lot of those, 2 to the n of those, leaf nodes. But basically, I can use the decision tree as kind of a enumeration of the values for every single possible joint assignment of x1 through xn. So that's interesting. That means decision trees are a very expressive hypothesis representation. That is, and this is a property in general that we like to see for learning systems. We like to have learning algorithms that, at least in principle, have the capability to represent any function that we might want to try to teach them. And one way to not have that property is to make up a learning algorithm that can't even represent every function. And so fortunately, decision trees have the property that they can, at least for these, if I have Boolean or discrete valued attributes and discrete valued y's, then decision trees can in fact represent arbitrary functions. So that's good. They're not restricted in the sense of being unable to learn because they can't represent. No, that's not a problem for decision trees. Okay, so here's a decision tree for real, learned on that medical data, that birth data from McGee Hospital. Because it's real and a little more complicated, it's presented in a different way. But the way you read this one is, we're trying to predict whether a mother will have a normal birth or a C-section based on features from the medical data. And this learned tree says that the first feature to test is the fetal presentation. That's the orientation of the baby right before birth. And if it's, there are 3 possible values, 1, 2, and 3. If it's in, let's say, presentation number 2, then, oh, I should explain these numbers. Up at the top, we have 1,000 different medical records. 83% of those turned out to be normal births, and 17% turned out to be C-sections. So what this says is, if you have fetal presentation 2, we only have 3 normal births and 29 C-sections. So your probability of having a C-section, if you sort to this branch of the decision tree, is 89% probability that you'll have a C-section. On the other hand, if you have a normal fetal presentation, then we go on to test other features, like, did you previously have a baby where you had a C-section? And is this your first birth, and other things like that. And so here you see a couple things. One, you see that we can in fact attach probabilities to the labels. So if we think of this discrete valued label as C-section or normal, here we're saying, well, we're not telling you exactly what it'll be, but we'll tell you that 73% probability you'll have a C-section, 23% or 27% that you'll have normal birth. And this is in practice a very typical kind of way of using decision tree learning. Okay, so now let's get on to the algorithm. Beautiful thing about decision tree learning, this is the whole algorithm. It's the world's simplest learning algorithm. What we're going to do is our learning algorithm is going to grow the decision tree, starting at the root, and just grow it top down until all of the training data is perfectly classified, and then it's going to stop growing the tree at that point. Okay, so we see, we have this loop that each time through the loop we're going to add a new decision node to the tree. And we're beginning with the root node. And for the root node, we're going to choose the best decision attribute to put at that node. I'll come back and say what I mean by best on the next slide. But let's just say we have some tests for choosing an attribute like humidity or outlook or temperature or windiness. We'll choose the one that's the best. If we can only use one, that's the best indicator. Then we're going to build that into, that'll be the decision attribute for this node, initially the root of the tree. And then for each value that can take on, say, suppose it's a humidity, which could be normal or high, then we create a new descendant for each value. If we put humidity as our root, then we're going to have normal and high as the branches. And we'll sort the training examples to those 2 leaves. all the ones for which humidity is high or normal, and then we'll look. And if these are all positive examples, we don't have to grow the tree anymore. We just label this leaf node positive. Similarly, if they're all negative, and if they're a mixture of positive and negatives, then what we're going to do is we're going to iterate. We go back, and now we set node to be that node which is the descendant of our root, which has a mixture of positive and negative examples. And now again, we just start and reapply the same procedure recursively to grow the tree below there. Okay? So it's a very simple, greedy, top-down growth of the decision tree using a test to choose the best attribute at any given point. So the actual kind of interesting next question is, how do we choose the best attribute? Suppose I have two attributes, A1 and A2, that I could put at the root of the tree. And suppose I have 29 positive, 35 negative examples in my data set. And if I sort on A1, then I get 21 positive and 5 negatives on this path and this other distribution here. And these distributions, if I sort there, how do I choose? So people have explored this question a lot. There are many papers that have been written on the question of what statistical test do we want to use here. I'm going to tell you the one that's most commonly used. It's also a statistical test that you're going to hear more about when we talk about other algorithms, like Bayes nets in this course. And actually, Nina had told me recently about some theoretical results that characterize some properties of this test. Maybe we can get her to talk about that later. But it's based on entropy. How many people here already know entropy? Okay, so entropy is, suppose I have a sample of training examples like those data for which play tennis is either yes or no. So some random variable like play tennis, some variable, and sometimes it's 1, sometimes it's 0. And let's say P plus is the proportion of positive times when it's 1. P minus is the proportion of times when it's 0, negative. Entropy measures how impure that set is. In other words, if it's all 1s, if I have a sample of 10, I guess we had 14 examples in our data set. If I have 14 examples and they're all positive, the entropy is actually 0. Or if they're all negative, the entropy is 0. But if they're half and half, then the entropy is 1. And here's what that function looks like. So if they're 0% positives, entropy is 0 because it's very uniform, very pure. Or if they're all 1. But if it's somewhere intermediate, then the entropy is non-zero. Entropy is an interesting quantity for a number of reasons. Here's the definition of it. H is entropy. If I have some random variable x, which in our case is that thing we're trying to predict, play tennis, is it yes or no? The entropy is just defined as minus the sum over all the possible values that play tennis can take on, 0 or 1, the probability that it does take that on times minus the probability that it takes that on times the log base 2 of that. Seems like an odd quantity, but it turns out one reason it's an interesting quantity defined that way is that the entropy is actually the expected number of bits we need to encode a randomly drawn value of x under the most efficient code. This is a very old and fundamental result from information theory. But basically what that means is, suppose that I have a pool of examples where play tennis can be 1 or 0. And you're on the other side of the room. and I want to encode in the fewest number of bits when I draw randomly from this pool and look at the value of play tennis, I want to now communicate to you is that value 1 or 0. And let's assume you and I both know what the pool of data is. We both know what the distribution of 1 and 0s is, but you don't know which one I've chosen. Now obviously you can see that if they're all 1s, and you and I both know that, it doesn't really matter which one I've chosen, and I don't even have to communicate with you what the label is, you'll know it. The entropy is 0. But if they're 50-50 1s and 0s, then when I pick one, I'm really going to have to use a bit to tell you whether I chose a 1 or a 0, because you know they're 50-50 and you don't know which one I chose. Well, if it turns out if they're 90-10, and I'm going to communicate a number of things to you, then I can get away with fewer than 1 bit on average. And the entropy is actually the number of bits on average that I can get away with. Basic result from Claude Shannon. Okay, so that's one thing that's kind of interesting about entropy. It's not essential to decision tree learning, but it is a property of entropy. And so let's see how entropy is used as the basis for the statistical test for growing the decision tree. And the answer is that we're going to use a quantity which tells us how much the entropy is decreased if I now sort the data on attribute 1 versus attribute 2 versus attribute 3 versus attribute 4. And I can try sorting the data on each of the different attributes and see how much the entropy is reduced. And then I'll pick the one that reduces the entropy the most, because that's going to give me the most pure subsamples. Okay, so one way to say this precisely is we take our definition of entropy. I can also define the specific conditional entropy. That is, I have the entropy of some random variable x, like play tennis. But I could also condition on the value of another attribute, like humidity. What if the humidity is normal or high? Then, well, if the humidity is high, I can say the conditional, specific conditional entropy, given that humidity is high, is just the same quantity, but now I'm only looking at the subset of data where humidity really is high. And then I can talk about the conditional entropy is just the weighted average of these, weighted by how probable it is that humidity is high versus normal. So the conditional entropy of play tennis with respect to humidity is just the sum over all the values of humidity, of the probability that we'll actually get humidity being high or low, times the entropy that we get when it is. And this is the quantity that we get if we sort on y. And so the final thing we want is actually, we want to choose the attribute to put at the root of our decision tree that takes the original entropy and reduces it the most. So we can look at the difference between the original entropy and the conditional entropy once we sort on attribute y. That's also called the mutual information, sometimes the information gain, between the variables x and y. And we just want the one where this quantity is highest, which in our case turns out also just to be the attribute where we have the minimum conditional entropy, since h of x is the same in both cases. Okay, so when we put that together, we do it this way. So we go back to our data set again. Then we can say, how do we select the root attribute for our decision tree? Here's the full picture. Originally in that data set we looked at, there were 9 positive examples, 9 examples where play tennis equals 1, 5 where it equals 0. That gives us an entropy of 0.94. You can work out the arithmetic yourself. But if we sort on humidity, which can be high or normal, that gives us a pool of 3 positive, 4 negative, entropy 0.98, and a second pool of 6 positive, 1 negative, entropy 0.59. And the weighted average of these would be 7 out of 14 times this, plus 7 out of 14 times that. That'll be the conditional entropy conditioned on humidity, which is this quantity. And then, so the reduction in entropy, if we sort on humidity, is 0.15. Whereas if we sort on this other attribute, the reduction in entropy is only 0.48, 0.48. Okay? So again, the point is entropy tells us how mixed up or pure the sample is. And what we're trying to do, we have some entropy in the pool of data training examples we're looking at. We want to pick the attribute that reduces that entropy as much as possible. And we take a weighted average of the entropies in the 2 descendant nodes weighted by their volume. Okay. So this is, now you have the full decision tree learning algorithm. It's actually that simple. And so if you apply this to those 14 examples, it chooses Outlook as the most entropy reducing highest mutual information variable, puts that at the root of the tree, sorts the examples then. Here there were 14 days, sorts them into these 3 buckets. Then the algorithm notices that this pool of data is already uniform, has entropy 0. And so it just makes that a leaf node. Says the answer here is play tennis equals yes. However, this pool is not yet uniform, and so it recursively chooses now a second attribute to put here. And the arithmetic here shows that we want to use something else. So then as we continue, that gives us this tree. And so you can see Outlook is up there. We end up with these pools of examples that have uniform, either all positive or all negative examples. And as promised, the algorithm grows the tree top down with a simple idea that at every point in growing this tree, we want to pick the attribute that will best separate the positives from the negatives. We use mutual information as the test for that, based on this idea of entropy, picking the attribute that reduces the entropy the most. And so then in the end, we end up with a tree like this. Okay, so these slides will be on the web, on our course site. Next time, we'll pick up on this, but I want you to think about a couple questions before then. One is there a better statistic than this mutual information to use, and what are the properties of this? Another question I want you to think about is, well, I'll give you the answer to this one. Is there more than one decision tree that would perfectly sort this training data? The answer is yes. There is more than one decision tree that would perfectly sort this data. The question I really want you to think about is, in that case, which one should we choose? And why do we like this decision tree algorithm and the choice that it makes? So we'll talk about both of those questions next time. Okay, thanks.